Welcome to another session of a reading group on the assumptions of physics. Today we're probably going to finish the chapter on experimental verifiability. Last time we saw how experimental verifiable statements lead to the topology. Essentially, each verifiable statement is an open set in a topology, and the points are the possible cases that are defined by those verifiable statement. And so today we're going to look at sigma algebras, which is sort of a companion to the topological structure that is more used in measure theory and probability theory. And so we'll start reading. So I need first, as usual, to share and then put the link in the chat. There we go.
All right. Sigma algebras. In the same way that experimental domains find a natural mathematical representation as topological spaces, theoretical domains find a natural mathematical representation in sigma algebras. The main result of this section is that a theoretical domain provides a natural sigma algebra on its possibilities. Like topologies, sigma algebras are fundamental in mathematics as they allow us to construct measures, for example, assigning sizes to sets, limits for sequences of sets, and probability spaces. It is again fitting that theoretical domains are associated to such a fundamental mathematical structure. Let's first review what a sigma algebra is. The general idea is that we have a set X of elements, which we call points, and we have a collection of subsets of X such that it is closed under complement and countable union, contains the empty set, and contains the whole set X. For example, suppose X is a set of 1, 2, 3, then the empty set singleton of 1 and set of 1, 2, 3 is not a sigma algebra, while a set of empty set singleton 1, set of 2, 3, and set of 1, 2, 3 is. The first one is missing the complement of singleton 1.
Alina?
Okay, definition 1.68. Let X be a set. A sigma algebra on X is a collection. This is sigma still, right? Just
Yeah.
uppercase sigma. Sigma X of subsets of X closed under complement and countable union such that it contains X. That's just the same thing as above. Note that sigma algebras are also closed under countable intersections, since these can be expressed in terms of complements and countable unions. In the previous section, we saw how each verifiable statement can be expressed as the conjunction of a set of possibilities. How the operations on statements can be expressed as operations on the verifiable sets, and how all the verifiable sets form a topology. The same is true for theoretical statements, with the only difference being that we will end up with a collection of sets that is closed under complement and countable union, since the theoretical domain is closed under negation and countable disjunction.
Okay, definition 1.69. Let D bar be a theoretical domain and X as possibilities. We define the map A from D bar to the power set of X, such that for each theoretical statement in D bar, I guess A returns the set of possibilities compatible with it. That is, A of S are all the possibilities X compatible with S. We call A of S the theoretical set of possibilities associated with S. Proposition 1.70. Let X be the set of possibilities for a theoretical domain D bar. X has a natural sigma algebra given by the collection of all theoretical sets, meaning sigma X is A of D bar. Then the proof. The theoretical sets for the certainty and the impossibility correspond to the full set and the empty set respectively. Formally, A of, I think that's certainty, is the set of all possibilities compatible with the certainty, which is everything, while A of impossibility are all the possibilities X compatible with the impossibility, which is obviously empty. Therefore, both the full set and the empty set are in A of D bar, since both certainty and uncertainty, well, certainty and impossibility are in D bar. The complement of the theoretical set corresponds to the theoretical set of the negation, and therefore it has a theoretical set. Formally, the complement of A of S is the set of all possibilities that are incompatible with S, which means they are compatible with the negation of S. So it's A of the negation of S. The countable union of verifiable sets corresponds to the verifiable set of the countable disjunction, and therefore it is a theoretical set. So formally, A of S1 or S2 is all the possibilities compatible with S1 or S2. So we literally just write that out. So this is the union of everything compatible with S1 and everything compatible with S2. So it's the union of AS1 and AS2. This generalizes to countable disjunctions, so even infinite. Okay. The collection sigma x, defined as A of all of D bar, is therefore a sigma algebra by definition, since it satisfies all its properties.
There is also a special link between topologies and sigma algebras, as one may want to construct measures and probability spaces on topological spaces. There is a standard way to construct a sigma algebra from a topology. This object, called Borel algebra, is the smallest sigma algebra that contains all verifiable sets defined by the topology. The sigma algebra defined by a theoretical domain is none other than the Borel algebra of the topology defined by the corresponding experimental domain. Let X and T be a topological space. Its Borel algebra is the collection sigma sub X of subsets of X generated by countable union, countable intersection, and complement from the verifiable sets. A proposition. The natural sigma algebra for a set of possibilities is the Borel algebra of its natural topology. Proof. Since the theoretical domain can be generated by a basis of the experimental domain, the natural sigma algebra can be generated by a subbasis of the natural topology. This means that it is also generated by countable union, countable intersection, and negation from the verifiable sets of the natural topology.
Can I ask a quick question here?
Yeah.
This construction, getting a sigma algebra from topology, does that work in general, or do we use any of the facts that, I don't know, we are like Hausdorff or second countable or whatever?
It works in general. You
Okay.
always have a sigma algebra.
Great, thank you.
This fundamental link between experimental domains and topology on one side, and the theoretical domains and sigma algebra on the other, is important for multiple reasons. From a practical standpoint, it guarantees that these mathematical tools can always be used in science. Since experimental and theoretical domains are general constructs, any branch of scientific investigation can use techniques and results from topology and sigma algebras for calculation or for characterizing the domain at hand. From a conceptual standpoint, it provides a Rosetta Stone, that is, a way to translate between the mathematical concepts and the scientific ones. It gives a precise scientific meaning to the mathematical tools and everything built up on top of them. Every single step in a calculation, every single argument in a proof can be given clear and possibly insightful physical meaning. It grounds the abstract mathematical language in more concrete scientific objects. This in turn helps clarify the science described by common mathematical tools, unearthing possible hidden assumptions or simplifications about the physical systems being studied. This connection explains why these mathematical tools have found such successful application in the physical sciences.
Decidable domains. We conclude this chapter by analyzing decidable domains, those for which we can experimentally test both the truth and the falsehood of all statements. For example, the domain for animal identification and the domain for the amount of money in my pocket can be considered decidable, as we can typically tell experimentally whether this animal has whiskers or not, or whether there's more than $1.50 in my pocket or not. Decidable domains have special characteristics and are easier to study. Since we can verify the negation, any theoretical statement is also verifiable. And since all theoretical statements are verifiable, so are the possibilities. That is, we can verify that this animal is a cat and that there are $2.30 in my pocket. As all statements can be expressed as a disjunction of possibilities, the possibilities themselves form a countable basis. For example, there is more than $1.50 in my pocket can be expressed as a disjunction of the appropriate statement of the form, there are X dollars and Y cents in my pocket.
If it's okay for me to jump in the order here. Definition 1.73. An experimental domain D sub X is decidable if all statements in the domain are decidable. Formally, for every S in dx, we have the negation of S's in dx. So proposition, let dx be an experimental domain. The following are equivalent. 1, the experimental domain is decidable. 2, the experimental domain and its theoretical domain coincide. 3, all possibilities are verifiable. And 4, the possibilities form a countable basis. So proof. To prove 2 from 1, suppose D sub x is a decidable experimental domain. As D sub x is decidable, it is already closed under negation, and therefore all statements in its theoretical domain D bar sub x are already in D sub x. To prove 3 from 2, suppose D sub x coincides with its theoretical domain D bar sub x. As each possibility is a theoretical statement, it is also a verifiable statement. So to get 4 from 3, suppose the possibilities are verifiable. Note that the possibilities can generate all other statements through disjunction. To show that x is countable, consider a countable basis B contained in D sub x. Because the possibilities are verifiable statements that can be generated from B by finite conjunction and countable disjunction. Moreover, since the possibilities are the narrowest statements that are not impossible, they can be generated from B using finite conjunction only. Since B is countable and x is generated by B through finite conjunction, x can be at most countable. Therefore, x is a countable basis. And so to get from 4 to 1, suppose the possibilities x form a countable basis, then each possibility is verifiable, and so is in their countable union. The negation of a verifiable statement can be expressed as the countable union of possibilities and is therefore verifiable. All statements in the experimental domain are decidable, and therefore the domain is decidable. Makes sense. And as the possibilities for a decidable domain must form a countable basis, their cardinality can't be greater than countable. That is, only domains that are non-decidable can have possibilities with cardinality of the continuum. In this sense, they are more constrained and simpler to study. Mathematically, the natural topology corresponds to the discrete topology, the one for which any subset of the possibilities is a verifiable set. That is, the topology is simply the set of all possible sets of possibilities. The cardinality of the possibility is therefore enough to determine the topology of the space, which means that one number is enough to characterize the space. It's a very nice result.
All right. A topology T sub x on a set X is called a discrete if it contains every subset of X. Theorem, decidability of is discreteness. The natural topology of the possibilities X for a domain D sub X is discrete if and only if the domain is decidable. Proof. Suppose D sub X is decidable. Let U be a subset of possibilities X. The statement S, which is, what is it? Disjunction, yes?
Disjunction, yeah.
Disjunction of all X in U is generated from X through countable disjunction. Since D sub X is decidable, X is a countable basis and S is verifiable. Therefore, U is a verifiable set and it is contained in the natural topology. The natural topology of X is discrete by definition. Now suppose D sub X is such that the natural topology for its possibilities X is discrete. Let X be a conjunction of X's and let S be a statement. Since the topology is discrete, U is part of the topology and S is verifiable. Consider its negation. So its negation of S is conjunction of X's which are in the complement of U. Is that right?
Yeah.
Since the topology is discrete, the complement of U is also part of the topology and negation of S is verifiable. This means that S is decidable. Since every statement in D sub X is decidable, the domain is decidable. Note, though, that discrete does not imply finite or vice versa. The domain for extraterrestrial life is finite, but it is not decidable as we cannot verify that there is no extraterrestrial life. The domain for the amount of money in my pocket instead is decidable, but not necessarily finite, as I could potentially have an arbitrarily large amount.
Okay, summary. In this first chapter, we have laid down the foundations for our general mathematical theory of experimental science. We have seen how it is grounded in the logic of verifiable statements, which is more limited than the logic of pure statements, as it has to deal with the practical constraints introduced by the termination of the tests. Okay, should we go through the picture or should I finish
Yeah, let's go through the picture. So the idea is that we started with the idea of statements, and we actually start with verifiable statements that are mapped to open sets. We have the theoretical statements that are the elements, the Borel sets in the sigma algebra, and then the possibilities, the cases, are defined, are the points, right? So you typically, mathematically, you start with this. Instead, what we did, we started with the statements. Actually, we started with the context and the verifiable statements because those are the things that are more connected to experimental verifiability. These are the things that contain essentially all the physics, and the theoretical statements and the possibility are there sort of to support and to close the space so that we can have a full algebra and do everything that we need mathematically, right? So this is the map, and now whenever you have a mathematical space, classical mechanics, quantum mechanics, field theory, and so on, it will always be a topological space, and there is always going to be this map, and you're always going to be able to give the same physical meaning to all those mathematical objects.
Okay, we saw that we can group verifiable statements into experimental domains, which must have a countable basis to allow us to test any statement within an indefinite amount of time. We saw how to construct theoretical statements to find all the theoretical statements that can be associated to an experimental test. And we saw how the possibilities are those statements that, if true, give a complete prediction for all statements in the domain. We have seen that because of the disjunctive normal form, each verifiable and theoretical statement is equivalent to a set of possibilities, and how logic operations and relationships become set operations and relationships. As such, the experimental and theoretical domains respectively provide a natural topology and sigma algebra for the possibilities.
I was supposed to go before, so let me just jump in now. What we have ended up with is a conceptual framework that captures the necessary elements of scientific practice and codifies them into a symbolic representation with a well-defined meaning. There is no guesswork as to what the points of our spaces are. They are the possibilities, the statements that provide a complete description for the domain. We do not have to provide an interpretation as to what the sets of a topology represent. They correspond to verifiable statements. All the objects have a clear definition and meaning from the start. We know which ones are necessary and to what extent they are physical or idealized. This will provide a much more solid foundation to the rest of the work, which will ultimately allow us to understand much better the fundamental physical theories and the connections between them and to other areas of scientific thought.
So I think sort of this is when I was working on foundations, trying to understand things. I realized that if we don't have a layer like this, you're never going to be able to sprinkle understanding on top. So this is, I think, what needs to be done to have something that is both crisp mathematically and then conceptually solid. So this is the end of the chapter. So I don't know if there are questions or comments or whatever.
I just remembered that you said sigma algebras are there to define limits of sets. I haven't seen that link before.
So both sigma algebra and topologies are useful to define limits.
Yeah.
So,
well, okay. So there's nothing special about, like, instead of limits of a sequence of points, I have a sequence of sets, and I want to find that limit. Is there a special connection to sigma algebras? The topology should be enough to define that, I guess.
So you're saying that topologies are more for defining limit of points, while sigma algebra are for limits of sets?
That's what I was getting from the comment in the introduction. I'm not sure if that's true.
I haven't thought quite it like that. So
okay, then I was just over-interpreting the comment. Okay.
I think so. It may be true. I don't know. Like the way that I think about sigma algebra, it's more for the limits of number that you associate to sets. So you have an idea of volume of a subset. So you have a space, you have a bunch of subsets, you want to define a volume, a size, and you have to do that on a sigma algebra.
Yeah, that makes sense. Yeah.
And what is interesting there is what is interesting for the sigma algebra is that it's sort of a bigger space. Like the closure has to be countable. If you try to make closures that are more than countable, you're not going to be able to define limits. So this is the typical thing that the power set of the reals is more than countable, and you typically cannot put measures on the whole power set of the real. You have to limit yourself to a subset, and that subset is going to be a sigma algebra, and it's not going to be a full set. So that's kind of one of the interesting bits is that we get nice structures because we only are interested in the ones that the elements, the objects that map to physically interesting objects. And if you get everything that you could mathematically define, then you get into trouble.
Wait, you said what has to be, the closure has to be countable so that I can define a measure, something like that?
Yeah, so the Borel sets of the real line, right, are all these sort of intervals that are generated by intersection, complement, and union from the open sets of the real line, from the open intervals, right?
Yeah.
And it will include a lot of sets like the Cantor sets and all the everything. But all these sets are measurable. You can assign a size that it's compatible with the idea that an open interval, the size of an open interval, is just the difference between the initial and the final element. But if you were to try to include all possible subsets of the real line, there would be sets that are not measurable. There are sets that you cannot define a measure in a way that is consistent.
So, wait, isn't the issue that okay, how does this connect to the closure? In what sense to be countable? Like the basis?
No, the closure of the sigma algebra, right? Sigma algebra is closed under countable intersection and countable union.
Okay.
Right? If you were trying to close under arbitrary intersection or arbitrary union,
yes,
you'll get into trouble.
Okay, yeah, that makes obviously sense. Okay.
Okay. For the topology, you are closed under arbitrary union, right?
Yeah.
But then you have finite intersection.
Yeah. Okay.
And so the idea in the topology, when you have something that it's not second countable, then the limits are not just defined by sequences, but you have something called nets, which are more complicated objects. It's basically, when you have a sequence, the index is a natural number. When you have a net, the index can be an arbitrary set. That's roughly how it maps. But fortunately, everything in physics has to be second countable, so we don't care, we can just use sequences. So, what do you guys want to do? So in principle, we can start the new, oh, this is just a table. So we could start the next chapter and go on, or we could take this time and morph it in something else. What do you guys have any preference of what would you like to do?
Maybe we could just have a review, just going to the table of contents to see what the chapter would contain, because I sometimes when the discussion becomes technical, it's how to say, it's difficult to find to get intuition.
It's gonna get more and more technical. So this is essentially this chapter is going to be about combining domains. So whenever you have a mathematical definition of a space, the first thing that you do is start creating maps and product spaces. So what we do here in the first section would essentially be, okay, I have two domains. What type of maps you can you define there? And what you're going to be able to define are two things. One is an inference relationship. So you have a statement in Y that you know how to verify. What is the closest statement in X such that when you verify the statement in X is actually the same as verifying the statement in Y. Right, so basically you have an inference between this statement to this statement. So if you have this relationship, then from Y you can infer always something in X. And this is a type of relationship. Then you have let's see, there should be a causal relationship. And now the causal relationship goes from X to Y. So if I know that a possibility in X is true, then a possibility in Y is true, then this is a causal relationship. So this causes this. And the main idea here is that causal relationship and inference relationship are the same thing. And it's more or less like this. So you have, this is water temperature, and this is the density. And this is the relationship that you have. If you have a statement, which means a set on density, you're able to infer a statement on the temperature. So if you know that the temperature is within here, then the temperature must be either inside this set or inside this set. And note that the inference relationship does not work on the other side. So if I know that the statement is here, this statement is not equivalent to this, because if I know that I'm in here, I could also be in here. So there is no equivalence between this statement and this statement. But there is a causal relationship. If I know the infinitely precise value of temperature, then I will know the infinitely precise value of density. So this chapter essentially goes through the details of all this, defines a relationship essentially both in terms of statements and possibilities, and show that you can go from one thing to the other. Then there is the combining domain, this idea of creating products. So if I have two domains and I want to combine them to create a domain that describes both things. So for example, I have a domain for the horizontal position, I have the domain for the vertical position, I put them together, and now I have the domain for both the vertical position and the horizontal position. So there is mathematically, we define what that procedure is for how to combine it. And then there are three cases that are of interest. One, if the domains are independent, which means for every possibility of x, you can have any possibility of y. And so the possibilities are basically just the Cartesian product of the two. You could have a domain dependence, which is the thing that we saw before. And then if you have a domain dependence, it's like essentially that one domain is a subset of the other, because every verifiable statement that is in here, it's also here because there is one that is equivalent. And this is the typical thing like we saw before. If you have water temperature and water density, one is dependent on the other. And then there are domains that are incompatible in the sense that either a possibility of one is true or a possibility of the other is true. And so this is a classical example here. I have the domain of plant identification and the domain of animal identification. Well, if something is an animal, it's not a plant, and vice versa. And what happens is that the possibilities are kind of like the disjoint union of the two. And the topology is the coproduct topology. And once we do that, then what you want to do is create the experimental domain for the experimental relationship. So I have x and y. I have the set of all the possible relationships between them. How can I construct one from the other, like the domain of possible experimental relationship from the two domain. And the main important thing here is that you are closed. You can show that the experimental domain of the relationship has still the properties of a standard experimental domain. It will have a countable basis and so on. So that's basically the overview of this next chapter.
And in the end, can we again find a correspondence to the standard mathematical structures? Like, for example, in the first case, we started with these verifiable statements and experimental theoretical domains, etc. And we ended up with topological spaces, this Hausdorff second countable, etc. So is there, again, some mapping in the end to something that a mathematician would know?
Yes. So, for example, you can prove that, where is it? There should be a proof somewhere. Basically, that the causal relationships are continuous functions. All causal relations are continuous functions. So the idea is you have a domain, so a set of points with a topology that is experimental verifiability. You have another one. And then if you want to have a map that makes physical sense, then the map has to be continuous. And it's really because if I am able to verify something on x, on y, right? So I have a verifiable statement on y, I can use that to to find something in X, and therefore whether I test on Y or I test on X is the same thing. So whatever open set that I had on Y becomes the reverse image is an open set on X. So all the things are set up like that. The topology of when you combine two independent domains, the topology that you get is going to be the product topology. If they are instead incompatible domain, you get the co-product topology. So yeah, they are all things that are meant to very easily then connect to standard mathematical structure.
So just to be clear, these maps are continuous, but they aren't necessarily open maps, as in like they don't necessarily send an open set to an open set, right?
Correct, yes.
Interesting. Okay. Oh, I guess because in the case where we had that graph that goes like this, you could have like an open set that's open on like the interval that goes right to the apex, and then
Yeah.
okay.
Yeah. And the interesting part, I don't have it, like I don't have the diagram here, I have it in slides, but it's really because when you look at the inference goes from the final thing to the initial thing. And this is why you get the continuous definition, where it's the reverse image of an open set is an open set. While the map, the causal map, is from X to Y. Maybe it's best to go back here, right? So the inference goes, I know something here, and I map it. I map it here, right? So the inference goes sort of in the inverse way of the cause. The cause goes from T, from the temperature to the density. Right, by the inference goes from a density to the temperature. So yeah, this is the beauty of these things, that all these things come naturally. So another thing, if you study topology, people talk about the box topology. So when you have a product of countably many or infinitely many topological spaces, the way that you have to construct the open sets is you take the Cartesian product of open set infinitely many spaces to construct the open set. And then in principle you could take the infinite, like the product of infinite open set, and that's called the box topology, and you basically just show that that's a bad topology and you shouldn't be using that. But you never have like a real motivation of why you pick the correct product topology. And here it's actually comes out of the construction, because what you do, remember, we just have statements. So all these domains are just statements. And we have the context, so we know how to put this thing together. So you just take those statements and you close under finite conjunction and countable disjunction. When you close by finite conjunction, you can take only one statement from each different experimental domain, finitely many, right? You can't go infinitely many. And so you essentially are taking the intersection of finitely many spaces on the whole Cartesian product, which means you are taking the product of finitely many open sets. So the requirement becomes the same, and when you do the closure in the most obvious way possible, you just get the standard definition of the product topology. So it's fun to see how all these things that one studies from the math side, they just come out naturally in the most obvious way. Now, of course, if somebody hasn't studied all those things mathematically, they say, okay, yes, it's that. But that's the fun is knowing where these things actually come from.
Okay, I have one question about domains and how to combine them and whether they're compatible or not. Because I can imagine that specifically in the context of quantum mechanics, there could be some non-obvious way, or at least, like, I don't know exactly, but I assume it should work just the same way, but then it might be not obvious what kind of statements we combine here, like statements about what can I measure about position, what can I measure about momentum, or something like that. And then they will be somehow issues when combining them. Like if I have a certain precision in X, I cannot get a certain precision in P. I don't know where this would show up here, if at all.
Okay, so you have to distinguish the statement of the variables from the statements on the states themselves.
Okay.
So imagine that you have the set of pure states, right, for a what's his name, for a two-state system. So we have the block sphere,
Yeah.
and the surface of the sphere correspond to all possible states, and it will have the standard topology that you put on a sphere.
Yeah.
So you could say, I have I have one of the states in this set, or I have one of the states on this set, and so on, right? So you can essentially delimit the possible state by putting any of the set on the sphere. But these are not necessarily statements that correspond to a single variable.
Yeah.
So if I said, if I want to say define spin up, right? So I have my sphere. Spin up is just a sort of a value that it's linear in the vertical direction.
Yeah.
So every open set, right, on the vertical direction becomes an open set, right, on the sphere.
Yeah. Okay. So I would make like the statements we were talking about would be like statistical statements, as in like in this state, if I measure like I get like the probability to get spin up is between, I don't know, 85 and 90% or something like that. And that would be
Yeah,
the
but
cut.
at that point, you can think it really as an uncertainty on preparation. So I prepared a spin up, let's say within 1%, right?
Okay.
And so you have a little disk,
Yeah.
and that represents the state that you know about the preparation,
Okay.
right? And you can imagine that you improve your preparation procedure, and you make that statement smaller and smaller.
Okay.
So again, you're assuming that you can make your preparation procedure, better and better and better, to the point that these uncertainties goes smaller and smaller and smaller.
Okay.
And at that point, through disjunction, you could prepare any possible set. Oh, I prepare this or that. I prepare that with this uncertainty, or these everything with that uncertainty, and then you're just making the disjunction of the sets.
Wait, so could I start with like just all statistical statements about spin up, and I would get just disks and rings and stuff? Well, if it's filled, it would be all disks. And then pick another like spin right or something like that,
Yeah, you can also do that, yes.
and then combine them in just the way defined here, and then I would get the topology on the whole ball.
Yeah.
Okay, I see.
So I don't know if this is a question that you were asking, or just a clarification that I'm asking about the stuff you were talking about. But in the case of quantum mechanics, you mentioned things like incompatibilities with like position and momentum measurements or something like that. Um, I guess the concept that I had in my head was that, like, well, we phrase a lot of the experimental statements here as like measurements of specific properties of objects, like the water has this density or whatever. But really what we mean is like the statement is given some experiment, the output will be within this range. Like something like that. Like this is the measurement of a specific setup of an experiment, not just like we know the properties of the water just because we know it. So like in the case of quantum mechanics, we wouldn't say a statement like, the position of this particle is between here and here, and the momentum of the particle is between here and here. It would be more like the output of the the thing that displays on my computer screen when I do this experiment that is supposed to measure the position of the particle will be between this and this. And so then you avoid the problems of like asking about conjunctions of statements about position and momentum, because like the statement that you're making is like this is going to be the output of some experiment, and if you try and do both measurements, you're doing a different experiment than just doing like one of the measurements, I suppose.
So this is where you have to distinguish that there are of what the assertion is about. So there are things like I don't know. Today is cloudy, right? That's a statement of a particular thing at a particular time, and that's just a data recording, and there is no sense of how can I say, like there is only one specific thing that you've done and so on. What is what we're trying to instead write scientific laws and all that. There is a sense of repeatability, so it's like every time I look at every time that I prepare a temperature in this range, the water density is going to be in this range. So this is more of an every time statement, right? Then I've done something in particular. So whenever we define a quantum system, a quantum states has to be the outcome of a repeatable procedure. So when I say spin up, it's not that this particle is right now is spin up. No, it's I have to have a procedure that sort of prepares that, because especially in quantum mechanics, if you just do a single take measurement, that's not telling you anything about the system that is coming in. Right, so if I have spin in an unknown direction, and then I measure spin in a vertical direction, and I say spin up, you don't know what the original spin was. In principle, you only know that it couldn't be at an infinite precision spin down, but since infinite precision doesn't really exist, that statement is not. So when you are making a measurement on ensembles, then the fact that each single, that at a specific time you can decide to measure one variable is irrelevant, because you're going to have, you're going to be able to re-prepare the system and then measure the other variable. Right? So if I have a consistent preparation of spin in some direction and I do not know the direction, then I make a bunch of measurement in, vertical measurement, horizontal measure, and measurements in Y. I gather statistics, and then I'm able to say, aha, the initial thing was within this range, right? So in that sense, the measurements that I'm making in this constant, the verifiable statement, are a verifiable statement on ranges of the statistical quantity. So I can say the expectation of spin up is within this region, the expectation of spin right is between this region, and the expectation of spin y is this region. And then you have three verifiable statements, you have three open sets, you back map them on the sphere, and now you get a region on the sphere. And the topology of the sphere can be generated with that. You take all the open sets on X, Y, and Z, you back map them on the sphere, and that thing is going to generate the topology of the sphere.
That makes sense. Yeah, thank you for the clarification.
So the fact that you have this incompatibility, like the quantum logic thing, right? It's not that you can't take the the conjunction and the disjunction of this statement. You can always do it on the statistical level. What you can't do is whenever you have so if you think of classical probability distributions, right? If I have disjoint supports, right? I can always find events. So let's say if I do not have disjoint support, right? I can always take that distribution and take the intersection of the two events and say either I have the common event or the part of one event that is not common or the part that is second event that is not common. And you can always think as the probability distribution as being the sum of these different distribution with over the disjoint region. And that's the thing that you can't do in quantum mechanics. You can't say, oh, I have an event in position and I have in momentum, and I will take the full distribution and think that it's made of for distribution on the different permutations of the ends and the knots. That's the thing that you can't do. And it's not a problem of the logic, it's a problem of the probability theory. Because in classical probability theory, the fundamental assumption is that all the points, all the possibilities are mutually exclusive. Either I prepare one or I prepare the other, that there is no event that it's in common. And when you think about quantum states, each quantum state is an ensemble, and it's not necessarily true that two different ensembles, that two different pure states, are two ensembles that are mutually exclusive, that they can only give you events that are mutually exclusive. That's the thing that fails. But on the topology level, on the sigma algebra level, it works exactly the same thing. This is the idea of quantum logic is just a mischaracterization. It doesn't follow from the details. And again, the problem is that you're trying to take some physical theory and trying to backport an interpretation on top without having clarified what is the base theory that actually is common for all this. And once you do that, the sort of things fall more into place.
Okay, maybe just to follow up. I mean, it was clear like we want to talk about statistical statements instead of statements like the spin actually is exactly up, or like,
Yeah.
So that makes sense. I'm just curious. Okay, so when we talk about a quantum system, let's say two-level quantum systems, we will somehow get the Bloch ball. Or the sphere. I'm not sure if it's important here to distinguish, but if that's a different topology, I guess, from like, a two-level classical system or something like that, or 2 degrees of freedom or something. I'm just curious where the fact that this is a Bloch ball, what structure here has to know about that, or maybe captures that? Is it that it's apparently not when we combine domains of like statistical statements I can make about spin up and spin right? Is it in like maybe the logical context that we defined like much earlier, or is it already, I don't know, kind of built in? I would assume that if I start with just statistical statements about spin up, I would just get like a line. Like I'm talking about like probabilities, right? I would just get one line. And the other about spin right would also be just a line or like a segment. And when I combine them, I somehow now have to know that they were both like come from a sphere. And I don't know what part would capture that. Does it make sense?
Yes. So what happens here in when you create the combined domain? Let's see if I can find the right little piece. Okay, so you're combining the domains, right? So you're basically just taking all the possible statements and put them together and close. And then you're going to find that the possibilities of a combined domains are a subset of the Cartesian product.
Okay.
So, for example, let's see if I have. So, right. So, suppose that you have, I think this is the population of rabbits, right? And you have the domain of the number of males and the domain of the total population of rabbits.
Yeah.
Clearly, you don't have the full space because the total population has to be greater than or equal to the number of male rabbits.
Yeah.
Right? Because these statements are not independent. If I tell you something about one, I'm telling you something about the other. So that's exactly what happens for if you combine all the different directions in spin, right? You are going to have correlations in the sense that if you know that the spin up is very high, then the spin left and the spin like in the y direction have to be low because you have a constraint that puts them all together. And so you see these constraints because when you're trying to make the ends of your bases, some things become impossible.
Okay.
So
And
the context knows
okay.
because when you're trying to put so each domain does not know, right? Each domain only knows about the consistency conditions and the logical relationship between its statement. But when you put them together, the overall context knows.
So do I need to provide like some other data that tells me what is compatible, what is not, that was not given before? Like I could happily, okay. So is there some kind of choice that I actively make when defining this product? As in like, okay, so there is not just one canonical product.
Correct.
Okay. This is where it comes in. That makes a lot of sense.
So this is where I said that there are three types of product. Well, at least three types of product. There are infinitely many. If the domain is independent, you're assuming that any statement on one domain is essentially compatible with any other statement.
Okay.
And then you just have the product. But if you have dependence, right?
Yeah.
Then the product is just the bigger domain. That's it.
Mm-hmm.
And then I said that there was the incompatible domain. Then you have the co-product. It's a set of possibility plus the other set of possibility. I don't think I have a drawing yet for that. But basically, it's like you're getting the vertical axis on one side and the horizontal axis on those side, and those two things disjoint are the set of possibilities.
Okay.
Yeah, but the key insight is that whenever you are combining domains, just knowing the domain individually does not tell you how to combine them.
Okay.
Like you can't just say they are independent because it's not true.
Yeah. Okay.
So, for example, if there was no, can say, if there was no correlation, like if you could have any value of spin, vertical and horizontal, right? There was no constraint, then you would have all the three-dimensional X, Y, Z space.
Yeah.
DHZ?
Hi, David. Hi, good evening. Hi. In a way, how you combine the domains, that itself is part of the statement of the things you want to experiment on.
It was garbled. Can you repeat?
Yeah, I'm trying to rephrase what you explained before, that the way that you combine the different verifiable domains is itself part of the verifiable the relationship between verifiable domains. It's something that itself verifiable, so which you can do experiments on. So when you say that the spin happens and whatever the three different directions of spin behave quantumly, it is exactly what we mean, that we combine them as it is in quantum theory, because before quantum theory was found, you had to give some statements about it, and that's exactly the thing you should have done. I mean, if you don't know, right, and you have an experiment, so it's exactly the same thing. You don't. There is no a priori combination.
Right. Yes. Yes. So if you don't know what the constraint of the whole domain. So, for example, let's even do a non-quantum example. Let's just take a pressure, volume, and temperature from thermodynamics. Right. At the beginning, you think, oh, maybe I can have all of this, and then you start doing measurements, and then you see that you can't really cover the whole space, and then you suppose, oh, there must be a constraint there, and then you make the theory and so on. Yeah. That's how it works.
Yeah, and I saw that you define finality and countability, and that's what make it possible to have the verifiable domain of all the relationships of verifiable domains, right? It's part of that. It's to be able to have that.
Yeah.
So you must have the finitely.
Yeah. When we do the domain for the experimental relationship, the fact that both domains are second countable will also mean that the space of continuous function is second countable, and therefore, so the only thing that goes on top that is an extra requirement is that you need to be able to test the whenever I have one thing, I have the other. So if I only know, let's go back here. If I only know how to test temperature and test density, that's not enough to be able to know that there is a relationship. I can only say, in this case I did this, and in this case I did that, and I see that the value are the same. You can only verify that there is a relationship if you're able to say, I've explored all these ranges of possible condition and boundary conditions, and whenever I do that, every time that I measure the temperature in one range, I see that the density is one range and vice versa. And this is essentially the main difference between observational science and non-observational science, experimental science, is the degree to which you can actually test these relationship, right? So we think we have relationship like this for stars, right? Because we say, oh, whenever we see the brightness, we think that there is this temperature and so on, right? But that's not enough to tell us that there can't be a star that violates those conditions. Then it's through the knowledge of other facts of physics that then you try to create models, and then you say, oh, actually this model predicts that there is this relationship, and that's sort of what informs you as to whether that correlation that you found is just a correlation or there is actually a cause.
Yeah, actually, in the astrophysics, there is in the last 20 years, they also every time, many times that they said, oh, there is something new that there is no way to explain it in the current models, and that every time you facepalm because you decided that everything you saw is everything that there is, and now that you have better equipment, then you can find out that there is more to the universe than that, which is much different than doing in the laboratory. As you said, that you can test the whole thing.
Yeah, so this whole chapter is basically these things in detail. So we'll have to decide whether we actually want through all the proofs and all the discussion or not. We can discuss that on Discord.
I think one good news is that this is like half the size of the previous chapter, so it should take less. And I saw that we took like 6 meetings to cover this first part. So if we have a bit of patience, we could finish it. And now knowing this final goal, I think it's much easier to understand, because if it's just the starting, then it might be a bit blurry of what we're going for. But yeah, we can discuss it later.
Okay. And the other thing is that we don't have to go through every single proof like we did. Some of these proofs are simple and might be illuminatory, but something like I don't know. Some of these might be because there are proofs that are just tedious that you have to go and you know, they just don't tell you anything. So if we went to the properties and quantities, for example, where we define real numbers from a verifiable statement, a lot of it is technical detail, and I don't think like if somebody is really interested to look at the details, yes, but otherwise it's. Okay, any other questions, comments? Then we'll close and I'll see you all next week. I don't think I have anything next week, right? Let me check the calendar. But yes. So, see you next week. Bye.
Bye.
Have a nice week. Bye.